All right, let's dive straight into this explainer and uncover the absolutely fascinating physics hiding behind the everyday mysteries of how we see the world. I mean, we are surrounded by these incredible phenomena that we literally just take for granted every single day, right? From the shifting shadows on the pavement to the clear reflection looking back at you in the bathroom mirror. But to really understand sight, we actually have to start with nothing. Picture this. You walk into a completely pitch black room. What do you see? Absolutely nothing. The objects in there, they're still physically present, obviously, but without a luminous object like the sun or a flashlight giving off light, things simply cannot be seen. Light is the fundamental messenger.
Section 1. Sorting objects. How light interacts. The crucial thing to remember is that if you hold up an object and you cannot see through it whatsoever, it's completely blocking the light. We call this entirely opaque. Think of a thick wooden door, a heavy book, or a brick wall. The light hits the surface and bam, it stops right there. It cannot travel through.
On the flip side, objects that let light travel freely right through them to your eye are transparent. Because those light rays pass through without getting scattered or blocked, you get a perfectly clear image of whatever is on the other side. A clean glass window or a clear plastic water bottle are perfect examples of this.
Then, right smack in the middle, we have translucent objects. These partially block the light and give us a sort of fuzzy, blurred view of what's behind them. So some light gets through, but it gets scattered on the way. Frosted glass or a thin piece of paper are great examples of this tricky middle ground.
You can actually test this whole concept yourself. Just by holding up a simple sheet of paper or a piece of cloth, you can immediately tell whether a material is opaque, transparent, or translucent, purely based on how much light actually reaches your eye.
Let's look at this breakdown and categorize a few everyday items together. A pencil or a solid rubber ball. You definitely can't view anything through those. Not at all. So they are solidly opaque. But look at a sheet of writing paper. The view is not very sure, right? Because it really depends on the thickness of the paper and the brightness of the light behind it, placing it firmly in the translucent category.
Section 2. Secret of shadows. What makes them?
You know, you might think you just need light and an object to make a shadow, but a shadow actually requires 3 very specific ingredients to exist. Obviously, you need a source of light. You also need an opaque object, like we just talked about, to block the light's path. But the third thing? It's almost always forgotten. You absolutely must have a screen, like the ground or a wall, for the shadow to be cast upon.
If you're shining a light on a friend outside at night, notice how the light hits them. But their shadow isn't just magically visible floating in thin air. It completely relies on having a screen, like a piece of cardboard or a building, right behind them. Take away that screen, and the shadow seemingly disappears into the night sky, even though the light is still being blocked.
But here's a fun question for you. Do shadows always tell the truth about an object's shape? We use shadows to gauge the time of day and the shapes of things around us all the time, but they are essentially just a two-dimensional absence of light. And that means they can easily play tricks on our eyes.
We've all done this, right? Making make-believe animal shadows with our hands. The exact same opaque objects, our hands, can be shifted and twisted to completely trick our eyes into seeing goats, birds, or dogs. By just changing the angle of your hands relative to the light source and the screen, you completely alter the shape of the blocked light.
Section 3. Pinhole camera. Capture the world.
It's honestly amazing, but we can actually harness these blocked light rays and build something incredible. With just 2 ordinary cardboard boxes and a piece of translucent tracing paper, you can capture projections of the outside world. Seriously, no digital sensors, no fancy glass lenses, you literally just need a tiny hole to let light through and a translucent screen to catch it.
Putting it together is a total breeze. You just cut a square in the smaller box, cover it with tracing paper, and slide it directly into the larger box that has the pinhole. By sliding it back and forth, you're acting as the focus. You're just finding that perfect distance for the light passing through the tiny pinhole to hit your screen and form a picture.
When you point this camera out at bright sunlight, you'll see actual, colorful images of the objects outside. But here's the crazy part. The images magically appear upside down. Oh, and as a bonus, this simple setup can even be used to safely watch a solar eclipse. But let's go back to that upside down part. Why on earth would the image project upside down? And for that matter, why do the shadows we talked about earlier have such sharp, defined edges?
Section 4. Straight line rule. How light travels.
What both of those mysteries are solved by one absolute fundamental principle of physics. Imagine looking at a candle through a perfectly straight piece of pipe.
You'll see it clearly, right? But if you bend that pipe even a little bit, the light completely vanishes. This proves that light only travels in straight lines. Because it doesn't curve around corners, the light from the top of a tree has to travel at a downward angle through the pinhole camera, hitting the bottom of your screen. The straight lines essentially crisscross at the hole, flipping the image entirely upside down. Mind-blowing, right?
Section 5. Mirrors and reflections. Bouncing light.
So we know light travels in straight lines. But what happens when those perfectly straight lines hit a shiny surface? If you flash a beam of torchlight at a mirror in a dark room, it doesn't just block the light. Instead, it intercepts those straight lines and redirects them, immediately bouncing off to illuminate a completely different part of the room.
The big takeaway here is that a mirror literally changes the direction of the light that falls on it. Reflections are simply straight lines of light hitting a specialized surface and being forced to change their path. When you look in a mirror, you aren't seeing a magical duplicate of yourself. You are seeing light that has bounced off you, hit the mirror, and traveled in a straight line right back into your eyes.
I want to wrap this explainer up with a really beautiful observation from the source material about those familiar dappled shadows you see under trees. Nature has actually been building its own cameras long before we were making them out of cardboard boxes.
Because light travels in straight lines, the tiny, irregular gaps between tree leaves act exactly like the pinhole in our cardboard box. They project actual circular images of the sun right onto the ground. So next time you walk under a tree on a sunny day, will you just see shadows? Or will you notice hundreds of tiny circular images of the sun? It really leaves you wondering what other magical physics are hiding in plain sight, just waiting for you to look a little closer.